It looked like a pilot in command. Sir, ready to fly.
सर कुछ तो ऐसा दिखाना पड़ेगा ना, फिजिकली आप आ नहीं सकते हैं तो फिर ऐसा ही कुछ करना पड़ता है और क्या.
The pilot is saying, no, all people should sort of sit on their chairs. I'm going to fly now.
No, I mean, just to share with you on a serious front, why I started doing this. When I was taking classes at IIT Jammu, virtually, the students were complaining. You are not using the, this particular mic. So you should use this mic, only then your voice would be audible. I mean, that was their feedback. So then I thought, let me purchase a separate device for this purpose only and use it for that purpose. That's what I started. And the coordinator is in line with me, You can see Dr. Upadhyay.
This is another ATC control. Like, if you are a pilot, she is the air traffic control. She will allow you to fly or sort of say land.
Absolutely, absolutely. She has a bigger responsibility.
She is in command.
Yeah.
चलिए सर, है ना? ओके, मैं
जी,
सुनता हूँ, है ना? अभी बंद करना है इसको. ओके.
Sir, let us start. So on behalf of Institute of Engineering and Technology, IET DAVV, I really welcome you, sir, in this faculty development program on cyber security. I feel honored in introducing Dr. Devesh Jinwala, Professor CSE, CV, NIT Surat. He has also been serving to IIT Jammu as adjunct professor since July 2018 to till date. Dr. Jinwala was former head, computer engineering, former dean, research consultancy, dean faculty welfare at SV NIT Surat. He has also served Daniel Felix Ritchie School of Computer Science and Engineering, University of Denver, USA, as visiting professor during July 2016 to June 2017. Information security and privacy issues in wireless networks are his main research areas, while general information security, privacy issues, software requirement specifications, using ontologies in software specifications, and resource discovery are also topics of his interest. I am happy to share that he has completed 5 research projects, and while one is still ongoing, he has more than 100 publications in reputed journals and conferences. He has presented a number of research papers in India and abroad. Dr. Jinwala has delivered expert talks at various renowned places more than 100 times. He has supervised 11 PhD students and few more are working under his supervision. We are fortunate one to have Dr. Jinwala with us. I invite you to, sir, for addressing the audience. Welcome, sir.
Yeah, thank you very much, and good afternoon to all again. Thanks for that, very generous introduction, I would say. So let us get back to the actual technical things, and I'll go into the full screen mode. Please let me know if at all my screen is visible or not, and I might disable the video because video would not be of any use now.
Yes, sir, it is visible.
Okay, thank you. Yeah, so the talk is about peep into machine learning in malware detection. So, talk is actually encompassing different areas as such, and that makes it more sort of challenging to present specifically in a targeted audience. Here I believe because this particular FDP is focusing on information security, bringing something about which is non-information security related, and then trying to figure out how to apply to solve some problems in information security is basically a challenge. That's what my perception is. Let us try to figure out how far we are able to go ahead. So the topics which I intend to go through is the background and motivation. I am calling it adversarial machine learning, but it could be machine learning also. So machine learning, I thought, would include adversarial aspect also, and I'll explain to you before we actually get on to the applications in malware. There'll be a quite generous introduction to the entire theme also, because we need to have a very complete picture in our mind, I believe, in order to figure out where machine learning could be applied for malware detection. We'll quickly review through the machine learning techniques, and then come to the bigger problem of machine learning for security. What is the motivation? A few of the use cases. I'll give you a laundry list of all the use cases which I was able to collect from the internet, but we'll talk about a few of them. Not all of them will fit into our format of discussion. And then we'll come to, after quickly reviewing the malware basics, we'll try to focus on the applications of techniques for malware detection, and in the process, what is the taxonomy for progress in malware detection, and why machine learning techniques indeed have to be applied. This why component for me is very close to my heart, because unless we are convinced about applying a particular technique for solving a problem, we should not be using that particular technique. So why machine learning techniques should be applied, that would be taken through. And we'll spend quite some time on talking about the important components there: feature extraction, feature selection, and then classification and clustering. More so classification, because clustering of late only has been started to be used. I'll only show the glimpse of the tools used for malware detection, because that is not my view. It's a view which I picked up from one of the papers, and so that view can be, it's a kind of movie in progress, because new tools which keep coming in. So we would only see a glimpse of the tools used for malware detection, and again the data sets for malware detection. I'll also talk about the first aspect which I'm showing here in the last bullet, which is additional issues and challenges, that is adversarial machine learning, and then we'll try to conclude. So security basics, I think in the first lecture I was able to see in the schedule, Professor Vyavahare might have taken you through the basics of security. Here I'm trying to just trying to review those things. Basically, if you see ITUT, the International Telecommunication Union, they have proposed a very standard architecture asking that security ought to be studied in these components, typically 3 components: the security attributes which one desires from any system, like encryption, confidentiality, and access control, and data integrity, and so on. The mechanisms to be used for building in those attributes. So the encryption mechanism, if I use digital signature, if I use message authentication code, they all basically are the mechanisms by which I'll get a specific security attribute. And there'll always be somebody in the real world who would want to disrupt these attributes from being offered. So I'll talk about those in terms of attacks and the threats. I'll make a list of those threats and see how can I still ensure the attributes to be offered. This is a very beautiful diagram again from ITUT, which talks about exactly one-to-one correspondence. So if I talk of authentication, then what does it provide? That is shown in this rectangle. And what are the examples of authentication? If we talk of confidentiality, then what is the goal of data confidentiality, and what is the mechanism which would offer confidentiality? As I said, encryption. So these are kind of ready to refer chart which would let you know that there are differing. What is takeaway of this chart? I'll not take you through obviously all individual points, but the takeaway is that we should note that there is no single point solution, which is very important. There is no single silver bullet which will give you all the attributes which you want for security, and you can rest assured. So there are different mechanisms which are used for different security attributes, which I think makes this entire field very competitive, very challenging. Of late, the security is extended in terms of privacy to cloud computing. So a typical security framework for cloud computing is what is shown again in ITUT's specific document, which is X.1601. I'm trying to show this again to emphasize one important point, which we'll be looking at later on, which is on the malware mitigation techniques which are cloud-based, and why we had to bring in those techniques, which is what would be related to this diagram. So this diagram has been shown here, and this is showing. This is from a textbook by Anderson, which is titled Machine Learning for Security. It shows the entire cyber threat taxonomy. What are various threats, and what are the consequences of those threats. So we would be interested in this particular aspect, malware. So different manifestations of malware are what are shown here. We'll revisit this later on in the basics. Well, before we actually again come to machine learning and applying machine learning to security, it's important to note that from secure software engineering perspective, now this field is again an upcoming field where we want to apply the software engineering principles to build security mechanisms. That particular viewpoint says that the approaches to device security mechanisms can be classified into two parts. One is what is referred to as a reactive approach, or one which is also could be referred to as security software approach, which is what we are familiar with for all purposes. Like we talk about firewalls, we talk about the encryption systems, we talk about authentication portals or filtering routers and network servers. We talk about protocols at the transport layer, protocols at network layer, and so on. All this basically are looked upon as the security software, because we are typically concerned with building software which will help protect some other software or some other system. So it's known as reactive approach to designing security. Why reactive? Because you react to an incident which occurs in the real world. And there are two critical shortcomings of this approach. The security of the application would depend completely on the robustness of the security software which we are devising. That is the fortress wall of protections that surround it. And the defense in depth protection themselves would be vulnerable. What we mean by defense in depth, it's one of the secure software engineering principle to build in security, which says security would not be thought of only at one level. Like we know that encryption would be built at the application layer. If you think in terms of TCP/IP protocol suite, then at the application layer you would have some cipher encrypting your data. I mean, something which we commonly read about WhatsApp, which says WhatsApp offers you end-to-end security. So that end-to-end is application-to-application security. In TCP/IP parlance, it means that it is end-to-end security. The application layer on one side is considered to be secure with respect to the application layer on the other side. But then we also have security at the transport layer. We have a protocol like transport layer security. At the network layer, we have a protocol like IPsec. We have security at the physical layer. Again, protocols like, if you think in terms of Internet of Things environment, then protocols like Zigbee, they come with their own security protocol suite built into, which is at the logical layer. So, and then there is a physical layer security, which I think you have had one or two talks on that. So that's again a different thing. So security is built in different layers, which gives you defense in depth. And whatever security mechanisms we build in security software, they themselves would be vulnerable. They are likely to harbor exploitable development faults, and then the adversary's task is sort of eased out because he has to focus only on that security software. This problem has been compounded with nation-state adversaries. The entire aspect of security attacks being given kind of infrastructural support, and therefore reactive approaches to security do not directly address the insecurity of the application layer level software. The application level software still remains insecure, but you try to build around, encapsulate that in application level software with security software, and therefore you would assume that your application level software is secure, which is what is one paradigm, and which is what is not desired. Instead, what is desired is the proactive approach to designing security, which is now labeled as software security. Instead of focusing on security software, we now focus on the security of the software which we are trying to build in. So software security, which says that we would anticipate and eliminate the vulnerabilities in the cyber system. We would sort of focus on remaining prepared to defend effectively and rapidly against the attacks. And to function correctly, these kinds of software solutions would require the security by design, so built into the software development lifecycle, which is what is known as secure SDLC. We have heard of SDLC in software engineering, but now we talk of SDLC, which is secure. So SDLC. And you would use whatever mechanisms which are required, but now they would be applied to the software while it is being built. And one of the strong pillar of this software security is what we are going to talk about, which is either using data mining approaches or machine learning approaches, basically using intelligent approaches to anticipate the vulnerabilities, to anticipate the problems or threats, and then to make the software secure. So PPDM or machine learning approaches protect data from being exploited by using intelligent techniques in cybersecurity applications. So we are going to basically focus on software security. That's the point which I wanted to be highlighted. What is machine learning? I mean, just a quick review through machine learning. It's the process of building scientific model after discovering knowledge from a sample data set or data sets. And it's considered to be the process of applying computing-based resource for the learning process to implement the learning algorithms, to predict the future outcomes by application of those learning algorithms. And formal definition, which says that it's the complex computation process of automatic pattern recognition and intelligent decision making based on training sample data. Various machine learning tasks, which many of you might be familiar with: regression, classification, clustering, association, rule mining, dimensionality reduction, generative models. We would be using many of these, so I'll not spend time now, but rather talk about them, how these are sort of manifested in security. When I apply machine learning to security, where classification is applied, where clustering is applied, or where dimensionality reduction is applied, that's what we would be focusing upon. So I just wanted you to recollect that these tasks still play an important role when we talk of applying machine learning to security and typically to malware detection. This, I think, is a beautiful picture which talks about the trends in learning in machine learning. And it says these trends can be looked upon into three categories: trends of the past, trends of the present, and trends of the future. Why these different trends? Because it depends on the availability of the training data and the desired outcome of the learning algorithms and the mechanism in which the learning algorithms are sort of applied, which is again more dependent on the availability of the training data. When I show you what trends are in past, present, and future, you would be able to relate with this aspect very easily. The supervised learning methods or the ensemble learning methods, where you collect different machine learning methods and try to have an improved sort of supervised learning method. These are referred to as trends of the past. Trends of the present, unsupervised learning method or semi-supervised learning methods, where you would use a task like regression, are trends of the present. And trends of the future are the reinforcement learning, active learning, and generative sort of modeling. These would be put in the form of trends of the future, which is again one form of manifestation of unsupervised learning method. A diagram which shows the panoramic view of machine learning in terms of what we talked about just now: supervised, unsupervised, and reinforcement. And the objectives in all three cases are different. You could see unsupervised, no training data is required. We talked about earlier that the talk about trends of the past, present, and future is largely depend on the availability of the data. So if there is no training data required, it orients to moves to unsupervised learning. Machine learns from training data, supervised machine learning, and machine learns on its own would be reinforcement learning. Again, a beautiful panoramic view of the machine learning, the three taxonomies and what are the tasks associated with those taxonomies. So classification or clustering or sort of discovery of a particular structure or sort of diagnosing something. So applying classification for diagnosis, all those things I think are beautifully shown in this diagram. So I just showed this. This we have talked about, I'll not go there. So let us come to machine learning for security, and we should try to talk about the real motivation. Before that, what are the actual use cases? Where is it applied? This is coming up as an important subject of studies, and what I've observed is many of the institutes have started offering a course, elective course on titled like this only, machine learning for security. And as we'll see, it encompasses three different sort of aspects. I'll talk about this as I proceed further. Before I come down to malware, so the size and scale of cyber attacks basically has increased in the recent years as a result of different factors. Because one of the factors is the improvement in the available resources, the machine power, the storage. There is a dramatic improvement in those, and so the scale of attacks have increased. But also because there is a growing reliance now of industry on digital infrastructure, and the difficulty of maintaining an adequate cybersecurity workforce for this purpose, that has contributed a lot. The increasing normalcy of cyber operations within international politics. What I referred to earlier is the state support for the attacks, cybersecurity attacks. That also has caused the cyber attacks, the number, size, and scale to increase. But as a result of that, there is now an increasing focus on how the cybersecurity professionals could add up to this increasing scale. And whenever human being is not able to sort of keep up the pace, then obvious reliance on machine is expected. So a very informal way, a very basic way, rudimentary way of convincing why machine learning. So we would say that simply because the number, every time we have seen, whenever human being is not able to keep up with the number, with the pace, then we would rely on the machine. So that's why machine learning. It's basically to answer the questions, the questions which could be, could machine learning allow the defenders to detect and intercept the attacks at a higher rate, much higher rate than it is currently possible using only human support? Could machine learning powered agents automatically hunt for vulnerabilities or engage an adversary during an unfolding of the attack so that adversaries is not able to scale up to other tasks? Engage an adversary would mean that he's not able to sort of focus on multiple aspects of attack. His attack is not multidimensional. That's what is the objective. Should policymakers view ML as a transformational force for cyber defense, or as a mere hype? Because when people start talking about applying machine learning, there'll always be a lobby which will say that no, machine learning will create this problem, that problem, and so that question also is put in here. The last question, the question which you are seeing now is talking about how different techniques like AI or ML or even deep learning can help in cybersecurity right now, and what is this hype about? But the last important point, which was shown the first in my content slide, the adversarial machine learning, which is why wouldn't the machine learning techniques themselves be employed to aid? I mean, they themselves be the target of the attacks. So adversary also would use these techniques to create new attacks. And so basically, when we talk of ML for security, we would try to figure out answers to these questions. I talked about tasks earlier. So here a quick review of the tasks which are going to be of important, ML tasks which are going to be of important in information security. So regression typically, which means we want to predict the next value based on the previous value. Regression is often referred to as prediction in machine learning. At its core, it would use the knowledge about the existing data, find out the patterns from those data, and then have an idea about the new data. Like, the features such as the total amount of suspicious transaction, the location of those suspicious transactions, that would determine a probability of fraudulent actions. So that's where regression or prediction is applied in information security. And this could be divided into two categories: conventional machine learning and the modern approaches for regression. In fact, that is what we would note later on, that when you apply to malware, if you read the papers, then there is a clear sort of demarcation which says when we apply machine learning, even that is to be looked into as applying conventional machine learning techniques or applying new machine learning techniques. If you apply, if you try to study in general malware detection at its higher sort of level of abstraction is also classified into two ways of detection. One would be conventional detection, another would be machine learning based detection. So a kind of it's a kind of recursive classification. We'll see that as we proceed further. Classification in information security, it's applied where we want to actually talk about. The best example is that of spam filtering. Separating spams from the other messages can be used as an example of classification. And this is what, this spam filtering was the first actually encounter of machine learning and security. Actually, this were the first machine learning approach applied to cyber security tasks. Clustering, unsupervised learning technique applied for forensic analysis in machine learning, because the course and consequences of the incident are obscure. So it would be required to classify all activities in terms of clusters of those activities. And the solutions to malware analysis of late, we would see, have been using clustering. So this is where we would be using these particular tasks in malware analysis. In addition, the behavior analytics, where application users cluster together, which exhibit similar behavior, so that it is possible to see if they belong to a particular group or not, is where clustering is actually applied. What is the perception? So before we proceed further, in general, ML for S, machine learning for security, ML for S, the perception is that machine learning can indeed help in solving most common tasks, including the regression, prediction, classification, as applied to information security. A wide range of specific tasks could be fully or partially automated with the use of machine learning, including vulnerability discovery, which is these days a hot topic. You would find numerous approaches being devised in sophisticated ways, numerous project proposals being submitted to funding agencies to basically propose application of machine learning approaches for vulnerability discovery. The deception, the attack disruption, these are, how can these be automated by the use of machine learning? And many of these possibilities would still require significant machine learning breakthroughs. That's what the perception is. Remember, I'm talking about what is the view of the experts about applying machine learning in security. But this would require significant breakthroughs. That is what is believed. And these breakthroughs, therefore, mean that machine learning would provide solutions in incremental approaches. The perception on the other side is also true that machine learning would never become the silver bullet. It would not be able to solve all the problems of cybersecurity. And one of the reasons therein is that the machine learning algorithms themselves would be susceptible to security attacks, and the adversary would try to apply the same algorithms, or adversary would try to bypass the ML-based security mechanisms. So hackers would be able to use ML to carry out their all nefarious endeavors. So it's unlikely that ML will fundamentally transform the industry, except for giving a few breakthroughs, which was also one of the perception in the earlier optimistic lookout at machine learning. But the real scenario is that ML can never be predominantly only one, offense biased or defense biased. Remember, proactive or reactive, which is what we talked about earlier, offense and defense. But it could subtly alter the threat landscape by making certain type of strategies more appealing to attackers or to the defenders, to both of them. So both of them will try to exploit the ML techniques. So what should we study and what should we discuss? Basically, what I want to point out at the end of this slide is that the takeaway is that if we want to talk about machine learning for security, we should start from the use cases. What are the use cases for applying the machine learning techniques for cybersecurity. In the process, many of the authors in papers have proposed that the conventional, 7 or 8 layered approach for cybersecurity would not be applicable here. They have proposed an improvised 4-stage cybersecurity practice model. I'll not go into those things because, we don't want to spend too much of time talking about only ML for security. So what are the use cases? And that's the reason why, even though I'm showing you the actual use cases, this entire laundry list is shown to basically believe that machine learning can be applied. There have been use cases for so many activities, including detecting malicious activity, analyzing mobile endpoints, automating repetitive security tasks, detecting SMS scams, then obviously in malware detection, email monitoring and against the bots, in AI-based threat mitigation, to sort of obviously correct the human errors. So analyze user behavior and the process behavior to close zero-day vulnerabilities, vulnerabilities which would be able to have their impact before the mitigation can be built into. So having a mitigation mechanism built into before it is able to get into an exploit. And for network protection, that is in the form of intelligent IDSs for application.
Sir, your voice is not coming.
वो शायद डिस्कनेक्ट हो गया मेरे ख्याल से रक्षा। हाँ, फोन करके पूछना चाहता।
I'm sorry, there was a power failure actually, and so I had to switch the network to. I hope I'm audible and the screen is visible.
You are audible, sir. अभी स्क्रीन नहीं दिख रहा है और आवाज आ रही है।
I think you need to share again.
Yeah, I'm doing that. So I think the screen also is visible now.
Yes, sir.
Yeah, so there are, collected here 12 different use cases, but we'll not look into each one of them. Only some of the interesting ones, because that would actually motivate you to attach importance to this particular topic, machine learning and security. The first one itself is very interesting. Machine learning to detect malicious activity and stop the attacks. So there is a firm, UK-based startup, Darktrace. They have their solution. They have proposed an enterprise solution for this purpose to keep looking at the malicious activity. And 2 illustrative cases are often given as the examples here. The first case is that of a casino in Las Vegas. So what the attackers did was as follows. This is the Washington Post article which I could see, which says that how a fish tank in a casino was used to sort of take the data, important data from the casino. Only thing is, this was limited by the attack mitigation solution which this firm Darktrace. So it advertises actually. Darktrace advertises that we were able to sort of prevent this attack from being further extended. But the attackers, what they did was they attempted to acquire data from this casino, but they used fish tank as the sort of object. And this was internet connected fish tank. So one would wonder, why should a fish tank be internet connected? But this fish tank had sensors connected to a PC that regulated the temperature, the food, and the cleanliness of the tank. So this was also automated. But what somebody did was somebody got into the fish tank and used it to move around into some location from where it could be connected on some other network, bypassing the protection. And through that, the data was transferred. 10 GB of casino data was actually transferred to a device somewhere in Finland. Dark Trace basically sort of detected this particular attack and prevented further damage. So they claim that using our machine learning solution, this attack could be prevented. This is another article which appeared in Forbes about the same scenario. So these are all available on the internet. The other one was the national health system of US, which was affected because of the ransomware WannaCry some years back, if you have heard. But Dark Force again says that their algorithms spotted the attack, and whoever were their clients, they were actually protected. So the organization of NHS, which was using their solution, it sort of prevented the attack from being populated. In fact, they claim that none of their customers were harmed by WannaCry attack because of the deployment of ML-based solution for protection to detect the malicious activities and to stop the attacks. So indeed, basically a motivation, trying to sell that ML is important. Very relevant, another scenario use case is to analyze the mobile endpoints, because if you look at the vulnerability scenario, if you look at even the malware scenario, then one of the popular target is now the target is shifting from the end user systems now to the mobile devices. So endpoint security now applied to the mobile devices. What is the problem? The problem is today's attacks, including the zero-day vulnerabilities which we mentioned earlier, they are executed at machine speed. Therefore, the threat detection engine also must match up that speed. It should respond just as quickly. And that's where the use case 2 comes in. How do we devise the ML-based solution for attack mitigation on only the endpoints, and specifically the mobile endpoints? And here also we have interesting case scenario. Actually, what is the way it is being deployed by the actual, the scenarios in the industry? The solution is often referred to as MTD, so machine learning based threat detection module, which uses a UEM, Unified Endpoint Management sort of solution, which is again a layered enterprise mobile security strategy to protect the endpoint devices. It can be extended to millions of devices. So the motivation for applying ML becomes very clear. If you look at the actual scenario, there are two leading mobile threat detection firms, as shown here, MobileIron and Zimperium. They actually have collaborated, and there is a good article again on Forbes which says 10 ways AI and machine learning is improving the endpoint security. So they are proposing anti-malware solutions which are based on machine learning and which detects the threats earlier so that these endpoints can be protected. The objective is to detect the device, to detect the network threats and the application threats, and take immediate actions to protect the data of the company which is using these solutions. And this scenario, if you actually look at the industrial startups, typically there are a number of firms which are offering different solutions. So frankly speaking, I have not heard of these names of these firms before I started studying this particular area of applying machine learning for security. So firms like MobileIron or Zimperium and Lookout, Skycure, Symantec is known, but Vandera, these are leaders in mobile threat detection. They also use their own ML algorithms to detect potential threats, which includes malware also. Like Vandera's engine, which is MIREAM, reportedly detected 400 strains of S-Locker ransomware, which targeting business mobile fleets. Then machine learning and antivirus and malware detection, obviously an important use case. The basic paradigm used is what is shown here. You would use training phase in machine learning with benign executables and malicious executables, and try to come up with a predictive model during the training phase, and the same model would then be employed in the protection phase to deal with the unknown executables and actually predict the executable as malicious or benign. So that's the paradigm used in the antivirus and malware threat detection. Then there is AI-based threat detection, and there are again ransomwares which are actually prevented by applying AI/ML techniques. There is something which is zero-day vulnerability, as we discussed earlier. The point to be noted is that there are different strategies which are used there. So Google and Apple, they are attacking this zero-day vulnerability problem not only by using machine learning, but now, but earlier they used to offer bounties to somebody who can attack their software. So they would get to know that there is some problem in their software, and they would offer that price to the person, but try to sort of build the particular protection for that software. The counter was shown by Arizona State University, where they showed that ML-based techniques can be used to monitor the traffic upfront and then predict the zero-day vulnerabilities. So those were some of the use cases which I said we would try to look at. Now let us come to the actual malware sort of aspects for handling with machine learning. Malware we know is malicious software manifested in terms of viruses, worms, trojans, spyware, bots, rootkits, ransomware, and so on. And the kind of security attacks which they can do, I think we all are aware about it. It's mentioned here only for the sake of completeness, but the figures which are shown here, they are pretty interesting. So data from Kaspersky Lab, this is published in their white paper, which says that 1 billion data was stolen in 2013-14 from financial institutions worldwide due to malware attacks. Another firm, Kingsoft, reported the average number of infected computers in 2016 was up to 2 to 5 million. Mobile malware variants increased by 54% to that before in 2017, and IoT attacks increased 600% with a particular botnet and due to DDoS attacks. So that's the reason why we have to think of the marriage of these two techniques. Why specifically malware detection and machine learning? The point which I'm trying to make here is that while we have conventional malware detection techniques, why do we have to talk about machine learning based tools, and why in machine learning also we have to distinguish between conventional and modern day machine learning? So, ML and AI powered anti-malware tools have actually triggered tremendous paradigm shift in dealing with malware. The evidence is again the number of papers published. So if you look at Google Scholar statistics, it shows that there is 95% increase in, with respect to 2015 in 2018 on the published data. The number shown is 7720, and this is 476% increase with respect to 2010. Why am I mentioning this? Not that in 2010 when the malware didn't exist, not that in 2018 malware didn't exist, but then the approaches to create malware has changed, as we'll have to note very shortly. So basically, the figures here show that there is an increased number of studies, and this increased number of studies is due to different factors like increase in public label feeds of malware, increase in computational power and reduction in price of the hardware, the evading of conventional mechanisms, conventional detection techniques by the new automated malware development toolkits, which is what we would focus upon as we see. These toolkits, they rely on certain techniques, instruction virtualization, packing malware in a way in which they can avoid being detected, exhibiting different behavior, polymorphism, emulating some other device, metamorphism, converting from one form to the other, to sort of write and change the malicious codes that would actually evade the conventional techniques and even conventional machine learning techniques for detection. So one has to move to the newer techniques. When I keep saying newer techniques, what I mean is those techniques which are built on different technologies of deep learning. So something like generative adversarial networks are more resorted to now or CNN are more resorted to sort of build malware detection and mitigation. Malware, how do they spread? They spread by the obvious process. We all have been victims, so we know how they spread. Downloading process, using vulnerable services, luring victims to deliberately executing malicious code on their machines. Some ways of spreading the malware. The taxonomy we already saw earlier. The concealment techniques used by malware. Those could be what I mentioned, what I glanced at some time back. The encryption mechanisms where malware would be in the form of an encrypted routine in order to sort of prevent manifestation. The attackers would, the key and the decryption algorithm would also be there. They would be used to decrypt the malicious component in the malware, but the attacker would use this new generated key and encryption algorithm and produce new versions of the malware to evade the detection. Packing, a technique by which they would be encrypted and compressed both in an executable file, and a phase of unpacking therefore would be necessary before you are able to detect them to reveal the overall semantics of the packaged program. The obfuscation. The obfuscation is something wherein the aim would be to hide the program's underlying logic and prevent others from having any related knowledge of the code. The typical obfuscation techniques include adding garbage commands, unnecessary jumps, etc. And the malicious codes and all their harmful functionality would remain incomprehensible until they are actually activated. So a potential danger to sort of implement any detection techniques. In fact, this was only yesterday. I have not included that in my presentation, but I read a paper yesterday which was talking about devising mechanisms which are bit level, because in obfuscation it was observed that the newer ML techniques for obfuscation, they were able to detect the obfuscation of the ML code. So what now the malware designers started doing was they would take the code from different apps in order to create a malware. Because this is from different apps, the byte sequence which would be used by the obfuscation detectors, they would not be able to detect it. It doesn't belong to one particular application. And so what is now felt need is required is that it should be built bit level instead of trying to sort of attack the malware obfuscation at the semantic level. What is required is it should be at the bit level, where the bits are then converted to semantics to be able to figure out whether the code is malware code or not. So another concealment technique I mentioned earlier, polymorphism, to look different every time. And again, it would use unlimited number of encryption algorithms. In each execution, a part of the decryption code would change, because of which different behaviors are exhibited. And a transformation engine is also embedded in the encrypted malware, so that the engine would generate a random encryption algorithm out of all the algorithms which it is built to use. And a new decryption key would be connected, which would be used to sort of create a different behavior. Metamorphism, different from polymorphism in the sense that this is the even more complex as compared to polymorphism. The malicious codes would change themselves so that altogether a new instance would be built, which would have no resemblance to the original one. And this would not have even a coding engine, transformation engine, which is associated with polymorphism. So in each transmission, the changes occur automatically in the malware source code. So the summary is that malware spread has actually increased because of various reasons, because of pervasiveness of computers, high proliferations of the net, increase in e-commerce, diversity and sophistication of malware samples. That also has increased. But very interestingly, the required knowledge to write and customize the malware samples, that has actually decreased. And the reason why it has decreased, because the entire process has become automated. So we have now automatic malware creation toolkits, which instead of writing a new malware sample, with a very cost-effective strategy, would refine the existing malware samples, slightly modifying them here or there, and bypass the scanner's detection. Techniques are being used. The ease of malware mutation process has actually resulted in the exponential growth of new malware file samples. One simple statistics which I saw in one of the papers, so I put it, figures only up to 2015, which basically show a dramatic increase. We are not interested in numbers, but if you compare them with the previous era, you are able to see a dramatic increase in the number of malware file samples. So what is the detection progress taxonomy? Detection progress taxonomy has actually evolved from signature-based malware detection. I would say it is conventional malware detection, to heuristic-based malware detection, again conventional malware detection, to cloud-based, somewhere in between the conventional and the modern, where because one found out that the resources were not available on the end user machine, the processing was moved to the cloud, uh, then applying machine learning techniques. So only 4 progress taxonomies have been shown here. In fact, these can be refined further. You could think of something which is based on the formal software engineering techniques like model checking. You could think of something which is specific to IoT devices. So IoT-based malware detection techniques. And so this refinement can further be increased. This shows the traditional sort of malware mitigation, signature-based techniques. I think all of us must be able to relate with this very easily. If you look at the steps in the diagram, it says step 1, the malware is released. Step 2, computer is infected. Step 3, this is submitted by the users that I have had suffered from a particular malware, and therefore then it is analyzed by the antivirus vendors, and then a signature which characterizes that particular malware is generated, and the signature base which is there in the anti-malware software is updated, and after that the spread of the particular new malware is prevented, because now the signature is built into. And obviously you would be able to realize that this process is manually generated, manually updated, manually disseminated, and therefore it is time consuming and labor consuming. It makes the anti-malware software tools less responsive to new threats, obviously. So this motivated to the intermediate step, which is heuristic based, where we, the malware writers basically applied the measures which we saw earlier to evade detection. They can bypass signature-based detection. So heuristics used some kind of previous observation, previous knowledge associated with the handling of the malware, and a heuristic would be used to detect the, to sort of analyze the executables, extract their features in terms of static and dynamic features, and apply either file-based or rule-based sort of detection process for identifying these signatures. So signature-based only, but used some prior knowledge in terms of heuristics. So till 2008, this was the most important way. Again, conventional mechanism for malware detection. The problem against heuristic-based detection was the same thing which we talked about earlier. The automated malware development toolkits, one example is shown here, Zeus, can allow anti-malware vendors create and mutate thousands of malicious code per day, which this would not be able to handle. This rate of generation can slip through such traditional signature-based or heuristic-based detection. So the new intermediate detection would be, instead of signature, this would be based on behavior. So observe the behavior of a program to conclude whether it is malicious or not. Just as we have had this category in IDSS, the anomalous behavior, some of those are listed out here, where we have adding or modifying user account, or disabling the anti-malware itself, or modifying the boot record, and so on. So these behaviors would be sort of documented, and the anti-malware would try to identify these behaviors from the executable. If at all this behavior is executed, then it would be treated as malware. I mentioned model checking. Model checking is a formal software engineering approach, which is basically applied in requirements verification as such. It believes in using a model, previously built model, to actually validate the requirements, whether requirements are correct or not in software engineering. That's how it is used. But this was also applied in malware detection, malware checking, but has not picked up actually. IoT and mobile-based, I already mentioned, the scenario is because of the proliferation of devices, because of a large deployment of the devices, handling the malware here was becoming difficult, and so some new detection techniques were required, so categorized as IoT and mobile-based. Cloud-based, if you look at the steps, you would realize first, users receive a new file which could be affected. It's not detected with the existing signature sets. The file is treated therefore as unknown. The file information or original files are collected and they are sent to a cloud security center simply because the end device didn't have those resources to process it. You required kind of faster response with which can be done from richer resources. So detection system is built into the cloud security center that would use appropriate techniques, typically a classifier, to predict the unknown file resting on various kinds of features. This detection system would generate the verdict of the unknown file, whether it is benign or malicious, and this would be sent to the end device, which could be a resource constrained device, which could then take appropriate action to tag the malware, tag the particular input data as either malware or as benign data. So resort is taken to cloud, and that's why it is cloud-based malware detection, which is what is proposed here. So why apply machine learning? The endpoint, again, the conclusion when we talk of why apply machine learning is the same, and that is all these techniques which we see, they would sort of generate malwares. I mean, the malwares would be generated at such a high rate because of the automated malware sort of generators, that these techniques would be found to be limited. So the notion of creating a white list or gray list or blacklist, gray list would be something which could be turned into either rejected or authenticated manually by the malware analyst. This entire process, even if it is cloud-based, that was found to be limited. It was found to be not working against the automated malware writing and creation techniques. Therefore, the need for using intelligent techniques. What techniques are applied? This shows a kind of taxonomy of machine learning techniques. And interestingly, you should see, even while I kept on talking about conventional techniques as signature-based, we are seeing here the malware detection machine learning techniques also tagged as signature-based. So in ML also we have signature-based techniques or behavior-based techniques, and they would use different machine learning techniques shown there for different purposes. K-means or naive Bayes or SVM. We'll talk about them as we proceed further. And so a broad taxonomy of ML approaches, they are shown here. Basic objective is to detect the malware. Signature-based, the basic framework is as shown here. There is a digital signature database. The only difference from the conventional one is that there is some sort of extraction of the features, the characteristics of the file which is received. And an ML algorithm would be trained first, and then in actual cases when a real data is received, it would be given to the testing part to detect whether something is benign or something is malware. So the advantages and weaknesses: this is easy to run, fast identification, broadly accessible, finding comprehensive malware information. But it fails to detect the polymorphic malwares, and replicating information in the huge database is costly. Therefore, the ML-based signature-based detection also doesn't work. Shows behavior-based. The only difference is now, instead of relying on signature, we are relying on the process execution. So behavior is looked into. The advantages: it would detect unconceived type of malware attacks, data flow dependencies, the polymorphic malwares, but storage complexity for behavioral patterns is more and time complexity is higher. So in general, the ML-based techniques which we would talk about would be talked about in terms of three aspects. You'll have a file sample set obtained from user clients. A few features would be extracted, as is the case with any ML-based sort of implementation. Think of applying ML task for a particular purpose. The objective is to learn. That learning has to pass through a typical number of stages. Here also it would pass through the same phases. And what we have is there is a file sample set from which the file feature extractor would try to extract the features. These features would be processed by either classification or by clustering, depending upon the requirement to construct the model. And then the malware detector would be used to sort of detect whether something is benign or malware. So ML-based techniques are capable of classifying previously unseen malware samples, identifying the malware families of malicious samples, and also of inferring signatures. The detection would be two-step process. One would be feature extraction, other would be classification or clustering. First, various features, like the features which are considered are shown here. We will not be going into the discussion of the features. The API calls or the binary strings or the program behaviors, they would be extracted using two methods, static method or dynamic method. We'll see those to capture the characteristics of the file samples. And then the machine learning, actual machine learning comes in classification or in clustering. This entire process of classification can again be divided into two consecutive steps, the model construction and the model usage. As you saw earlier, the training phase and the testing phase. So in construction, the training samples are used, including malware, actual malware, and the benign files. These would be used, each sample would be parsed to extract the features representing its underlying characteristics, and the extracted features would be then converted to vectors in the training set. These vectors, the feature vectors and the class label of each sample, whether it is malicious or benign, that would be the class label, would be used as inputs to the classification algorithm. The classification algorithm could be one of these: ANN, D-tree, forests, support vector machine, and so on. It could be furthermore. I have not written all of them. And by analyzing the training set, the classification algorithm would build a classification model or a classifier. Further, during the model usage phase, new collection of unknown file. Now we talk about usage. New collection of unknown file samples, which could be either benign or samples, malicious, would be presented to the classifier generated from the training set. Note that the representative vectors of the new file samples, they would be first extracted using the same extraction techniques as we have used in the model sort of construction phase. And then the classifier would classify the new file samples either as benign or malicious. The metrics would be same as those in case of a typical machine learning system. That is either, you would be interested in figuring out the result is whether true positive, that is the number of file samples are correctly classified as malicious. True negative, that is the number of file samples correctly classified as benign, or false positive and false negative, wherein the number of file samples would be wrongly classified as malicious or wrongly classified as benign, respectively. Then you would be interested in finding out the true positive rate and false positive rate, which would be based on the above statistics only. So TP upon TP plus FN and FP upon FP plus FN would give you these two rates, and the accuracy, that is TP plus TN upon TP plus TN plus FP plus FN. So where you have gone wrong, all these factors would be taken into account in coming out with the accuracy. These would be the metrics used for evaluation of the classification algorithm. The metrics also would be measured either in cumulative or interactive fashion. The cumulative approach would measure the performance of malware detection at the instance level, that is at per file level, while interactive obviously would be for each interaction. So it is at the transaction level, considering different user bases. Clustering, on the other side, the graph here shows the basic pattern. Many of the things here also remain same, except for the main operation of clustering, wherein the similarity calculation of the traffic contents and the traffic behaviors would be based on certain different parameters as compared to that in the classification. So clustering can be used to automatically group the malware samples so that the similar behaviors can be grouped into the respective groups. It's based on using certain distance or similarity measures to allow automatic malware categorization. So what is up next? we would now focus on the feature extraction. So each of these phases, details of those phases. This is typically conventional machine learning only, but wherever required, how is it applied to the malware detection? Feature extraction, it would sort of extract the patterns used for representing the file samples. Typically in literature, if you see, most of the papers talk only about the PE files, Windows Portable Executables, because they are considered to be more susceptible to the malwares. Although the 2020 and 21 figures said that macOS also, the rate of malware in macOS has increased dramatically in last 2 years, and the reasons are not actually known, which could be attributed to the working in online manner also. That's what I read in one of the articles. The cause is not actually found out. Mainly two different types of feature extraction are used in malware detection, either static or dynamic analysis. In order to identify patterns in the input executable, one would actually have to do the analysis of the executable. So this analysis also would be done with respect to the time in two cases. So static analysis would be done without executing the executable WPE files. The target of static analysis could be therefore binary or the source code. Hence, a PE file would need to be decompressed or unpacked first. Remember earlier we saw, in order to evade malware, what adversary would do is he would try to sort of employ some concealment strategy, packing or encryption or obfuscation. So this would be required to be decompressed or unpacked first if it is compressed by third-party binary compression tool. Then it would be required to be decompiled with to the Windows executable. So typical tools used for decompilation, the disassembler and the memory dumper tools are used. These tools would be used to obtain protected codes located in the main memory, and then they would be dumped into a file. So we consider these to be static analysis. The detection pattern used in static analysis can then be extracted, which could be, what are the metrics used, what you would be interested in detecting, what are the number of API calls made, what are byte engrams in the code, strings used, the opcodes, the control flow graphs, and so on, which is what is shown in terms of this diagram. The features taxonomy. How do we classify these features in the input executable? What you would be interested in sort of classifying, that is what is shown. The strings or the engrams or the opcode engrams or API calls or entropy based or function call graph based static features or control flow graph features, and so on. Static analysis may also deal with some other features as compared to what is mentioned here, that is file property or file source information and export table. The static analysis advantages and disadvantages, again, they are similar to those which would apply to any other method which could be considered to be static. So the advantage obviously is that it would be able to explore, investigate all possible execution paths in malware sample, because it is done statically on file level. So it is exhaustive in detecting the malicious logic. It will not suffer from the coverage problem that dynamic analysis suffered from. We'll see what coverage problem is in dynamic analysis. And the analyzer's machines cannot be attacked by the malware under the study. However, the obvious drawback, because of the obvious above reason, is that it would include a lack of support for runtime packing of the code and the limitation related to complex obfuscation, one which I mentioned some time back. So if I have device static analysis for the general byte level kind of semantic level sort of analysis, then I'll not be able to take it to a further deeper level at the bit level. So in case the obfuscation is done from different application codes, then this analysis might fail. And therefore it would complement dynamic analysis and static analysis. They would complement each other because of the reasons, the similar advantages, disadvantages with respect to feature extraction would apply to dynamic analysis also. Dynamic analysis are those extracted from the execution of the malware instead of from the content of the malware, as we content of the executable, as we saw before. The analysis involves monitoring malware and observing the real sequence of instructions executed or the sequence of the calls made, or examining the system after the malware is executed. So it would reveal configuration or environment dependent information like process creation, file manipulation, registry manipulation, modification of memory values, and so on, modification of register values, variable values, and techniques such as auto start extensibility points, function parameter analysis, function call monitoring, information flow tracking, instruction traces. If you simply look at the names of these techniques, then also you would realize they talk about behavior. Like when we say function call monitoring, we are monitoring the execution of a function call. Information flow tracking, we are trying to track the flow of information. Instruction traces, we are trying to see the trace of instructions actually executed. So all of them, they point to the behavior and therefore dynamic analysis. The techniques used would be debugger, simulator, emulator, virtual machine. Advantages and disadvantages. Obviously, configuration and environment dependent information could be handled now, which were not handled by static processes. Useful in analyzing the packaged malware also, because that would be handled at the time of runtime unpacking, and the original code would be in the main memory. Can extract hidden code by tracking the newly written memory areas of the malware program, even if it is hidden through multiple layers of compression and encryption. But the problem is limited coverage, because one execution session, it would cover only whatever can be explored in that execution session. When you go on to a new session, then again, new things are to be covered. So coverage, which in case of static analysis, with whatever input which was given to it, was completely exhaustive. That exhaustive coverage applied to dynamic features is not possible in dynamic analysis. That is the limitation. And therefore, it is often looked upon as the approach for feature extraction which is desired is the hybrid approach, which says neither of static or dynamic would be able to solve the entire problem, and so integrate both of them. It would sort of have the respective advantages of both static and dynamic, and therefore the example shown here, packaged malware is required to first go through the dynamic analyzer, where the hidden code which was not found out by static analysis would be found out, as we just saw in case of dynamic analysis, and then the runtime execution would be analyzed. The runtime execution of the malware also can carry on, and then the hidden code bodies could be analyzed by static analysis to exploit the advantage of full coverage. The other novel aspects about feature extraction is using the semantics of the file content to represent file samples. That is, malicious behavior can be described using templates. The instruction sequences where variables and symbolic constants are used. These are based on the extracted features, that is semantics aware matching algorithms. Remember, semantics means meaning. So an algorithm, matching algorithm, which tries to look at the meaning of the file content. This is what is proposed for malware. This also is proposed for malware detection. And the relationships among different file samples may imply their interdependence. So whatever we talked about till now, which was looking at only one set, would not be applicable if at all interdependence exist. So it can provide critical information about their properties and the characteristics. That is, files legitimacy can be inferred by analyzing its relations, co-occurrences with other labeled benign or malicious peers. That is also looked into in some of the newer feature extraction techniques. The commercial examples, if an unknown file always co-occurs with many Trojans, then there is a high possibility. We are talking about interdependence of different file samples. So there's a high possibility that this particular file is also, helping in sort of those malware spread, and therefore it's a malicious Trojan downloader. So that's how this relationship between different file samples would be exploited through interdependence to identify whether something is malware or not. Commodore's anti-malware software behaves in this particular fashion, as it claims to look at file relations and file content both for malware detection. Symantec AM products, Microsoft IE, they have started using the features beyond file contents for malware identification. The other novel aspect, these features provide only an abstract view of the malware. That is, they use a particular, they are used by a particular classifier like a neural network, or as we'll see further, dysentry or support vector machine. The feature engineering and feature extraction, they are actually time consuming process, because you have to identify the characteristics, convert them into feature vector, and so on. So newer ML solutions for malware detection have started using, they have started moving towards deep learning architectures. The most recent one, as I mentioned before, generative adversarial network-based feature extraction and classification. In addition, malware detection should also include multiple modalities. Whatever we saw just now didn't specify anywhere multiple modalities. We'll not go into that, but I'll show it by means of a diagram. So what multimodal learning means, the studies which are able to interpret different signals together, different file contents together. So combining different modalities or types of information, they would improve the performance, which appears to be intuitively a very appealing task, but it's very challenging to combine this different levels of noise and conflict which may be there between these modalities. So a diagram which basically shows doing fusion when you have different feature vectors. You are trying to exploit different feature vectors instead of being dependent on a single feature vector, because we are talking about these as multimodal. So the classifier will have to work on combination of all of them. We have techniques like early fusion strategy or late fusion strategy, which does its work after classification, or intermediate fusion strategy. But I'll not go into this multimodal approach for feature extraction beyond this point. The step after feature extraction is often, an intermediate step is often introduced, which is known as feature selection, before we go to classification or clustering. So why feature selection? Feature selection is the process of selecting a subset of relevant and informative features from those which have been actually identified in feature extraction phase. Large collection of features for use in the model creation. The central assumption is that the data contains many redundant or irrelevant features, and therefore these have to be eliminated. Whatever is irrelevant, that must be eliminated. While elimination, there should not be any negative impact on the later classification or later prediction performance, because that would kill the purpose of doing classification in the first phase. So which features can be considered to be redundant? Which features can be considered to be irrelevant? Remember, these two are two different terms. So redundant features are those that would provide no additional information beyond what is already provided by the currently selected features. Recollect the redundant aspect used in typical DBMS concepts. A particular data is considered to be redundant when we say that the same information as is provided by that data is available from somewhere else. So here also this feature which provides information beyond what is actually provided by the available features, currently selected features, that would be redundant feature. Irrelevant are those that do not provide any new useful information in the given context. Whatever context is used, it's not providing any new information. So that is irrelevant feature. And what is irrelevant could be dependent on the specific application being considered, because in one application, something could be relevant, which might be relevant in the other application. So need for feature selection, therefore, is motivated by the fact that the number of features, they have to be reduced, and the number of features could significantly exceed the capacity of the underlying machine to process within reasonable time. Remember, there were two recourses to this. One recourse earlier we saw was to be dependent on a cloud infrastructure. So delegate this task to the cloud, because the underlying machine cannot handle the number of features extracted. The other recourse is to sort of reduce the number of features. So one is done at the algorithm level, other is done at the implementation level. Classification performance or reduction in classification errors, this also could depend on the ability of the system to quickly identify the most representative, most important features. And this entire process can be computationally intensive in terms of both memory and CPU time. that is to construct the required model for each and every extracted feature. Like when using n-grams, the number of features generated grows exponentially with n. So malware classification methods would basically introduce one more step, and that is feature selection, which is basically dimensionality reduction, which we saw earlier, if you recollect, as one of the machine learning tasks. The goal is to improve the compactness of the feature representation. Two approaches in feature selection: forward feature selection, which the process actually starts with an empty feature set, and new features would be added successively to the set to arrive at a reduced set. So be careful in selecting the features upfront. While backward feature selection, the process would start with all the available features and successively remove those which are found to be irrelevant or redundant. Removal of features or addition of features are usually performed based on certain selection criteria. So these selection criteria could be based on ranking the features based on their estimated discrimination ability. Ultimately, why we are interested in features? We are interested in features so that they can be helping in classification. So we want to remove certain features, something which doesn't help in discrimination, that could be eliminated. Thus, independent of the direction of the search for features to select, the key consideration would be how the feature subsets are evaluated for inclusion in the selected subsets. And there are three major approaches used for feature subset selection. Feature subset evaluation for selection, I would say. The first method is known as filter method. Second method is known as wrapper method. Third is known as embedded method. This aspect comes in feature selection for malware detection. Filters would determine the best feature subset by using statistical approaches. That is, each feature would be scored individually on certain specified criteria, and the feature would then be ranked. We want to sort of employ some statistics. So they would be ranked based on those scores. And then the feature selection is done merely based on the highest ranking. So based on this ranking. Alternatively, subsets of features could be selected by computing some quantitative measure of the discriminative capability of the feature subset. So whatever is the discrimination power, that would be represented in terms of some numbers, and then the feature subsets would be ranked, and based on that, the features would be sort of selected or not selected. Filter-based strategies, therefore, consider the features as being independent of the later classification stage or of the specific prediction problem being addressed. So whatever ranking which could be adapted in classification, that would be independent of the feature selection done here. These are generally fast, but still often capture the essence of the feature sets, and the independence from specific method used for later classification, implying that the filters could provide a powerful mechanism for pre-processing before actual prediction or classification is performed. So something that is supposed to be actually done later on, that is kind of done as a pre-processing step here. And some of the statistical measures used are shown here. The document frequency, information gain ratio, will not go into these. The wrapper methods, the second method for feature selection, the actual classification or prediction is used to evaluate the performance of different feature subsets. That is, a candidate feature subset is used to perform the required analysis. So whether classification or prediction, classification or clustering, that is actually used here. That analysis is performed here actually as a wrapper, and then the feature is selected. So the performance in analysis task using some training data is used to evaluate the feature subset, and clearly training a new model for each given feature subset is computationally intensive. Some computational intensive task which was going to come later on, what we are trying to do is we are trying to bring in before and do the task here. Therefore, the challenge is here to see how the subsets chosen are sort of efficiently reduced, and still we maintain a good performance in terms of robustness and the accuracy. So for a given classification algorithm, the wrapper approach often leads to the best performing feature subsets because of the computational intensive, like it's like spending something more in order to sort of gain something later on. The general applicability of the approach, independent of any specific classification problem, sort of tries to have some sort of additional capability built into, because you might employ some other classification algorithm, but here you're trying to aid that classification or clustering algorithm by doing selection. And the third method is embedded method. Feature selection is performed as part of the model construction process. Remember, whenever we want to classify part of that, the feature selection is performed. So embedded method is usually specific to a given classification because it's part of the classification, and therefore they would be generally slower than the filter methods, but provide some robustness and classification performance. So we are on feature malware detection. What we talked about first was feature extraction. Then we talked about is feature selection. And now the actual main goal, which is feature classification. So, one can see this in terms of the diagram which we saw earlier. Whatever we did earlier was to facilitate the actual intent, actual purpose, where you build a training model for being able to consider something as a malware or not, classification. So after the feature extraction and selection, each file sample is now represented in feature space using the extracted feature vectors and some label, because those feature vectors have to be labeled. Classification would then be performed by using the feature space generated from the sample training set as the input to a learning algorithm. By analyzing the input vectors, the learning algorithm would determine the parameters and the factors that are to be applied on the feature vector for further classification. And the feature vectors then would be classified into those predefined classes. So how is this? How is that set after this? This is what we talked about was training set. How is the testing set prepared? The testing set would contain a separate collection of malware and benign file samples. And similar to training sample, representative features would be extracted from each test sample. And then each sample in the testing would then be classified as either benign or malicious, the actual classification, using the same set of parameters and factors determined from the training samples. Classification is performed by using the feature space generated from sample training set. As I said, this is duplication. So what are the feature classification techniques used? I'm not trying to take you through all the sort of mechanisms used for classification, but some of the representative ones, which actually I saw them as being used in a number of papers on malware detection. I'm not cited which papers, but if you trace those papers through 2008, then you would realize that the features, the classifiers which we are seeing here, namely the decision tree, the random forest, and ANN. These are the ones which are prolifically used in the classification. So decision tree. Decision tree is a simple tree. The basic operation is also like a tree, wherein the internal node would represent the input variable, that is the features of a data set. The branches would represent the decision rule, and each leaf node would represent the class label. So when we reach the eventual leaf, then we would have been able to classify something as either malicious or benign. If you look at the diagram, then that is with respect to a typical HTML page, not with respect to malware, but with respect to an HTML page like LFrame, we would consider that to be either hidden or invisible or visible. So the branches represent the decision rule. My decision rule here would be to detect this as either hidden or visible. And then I'll try to look at whether it is from foreign domain or domain is blacklisted. If it is from foreign domain, then whether that foreign domain is, whether it is actually from foreign domain, in that case, I'll tag it as malicious. In case the domain is blacklisted, I would tag it as malicious. If it is not blacklisted, then I'll tag it as benign. So whatever the technique which is closest to the human behavior of classifying something, one would say, that is what is reflected in the decision tree. And therefore, if you look at the entire path from root to a leaf, that would capture the sequence of feature values which have been evaluated for each given variable on the path, because for each of the stages, you would try to evaluate the feature and then see whether we reach a particular classification or not. A greedy heuristic scheme is often used in practice to generate the tree using the input data, for instance, by splitting the features or variables using the expected parameters like information gain. And the problem which comes in here is that of overfitting. So that is handled by pruning, by reducing the tree. With the principal splitting of the nodes based on feature values, the decision tree can be easily represented or implemented in the form of simple rules. As I said, there have been numerous papers which use decision trees and show good metrics of evaluation for malware detection. One of the technique proposed to improve the limitations of DT is the random forest, and this also has become very popular in recent years. So far as, let me again emphasize, conventional machine learning techniques for malware detection are concerned. That means the position which I am taking, the picture which I am trying to present is, when I use decision tree, when I use random forest, we are talking about using malware detection by applying conventional machine learning techniques. So still we are not talking about using the modern machine learning techniques for malware detection. What is the difference in case of forest? The forest is something which is a collection of decision trees, obviously as per data structure referred to as a forest. So classification would be done within each forest, different classes would be obtained, and then some way of combining these would be used, which is shown here as majority voting. There are different paradigms used in case of random forest for both these purposes, for splitting as well as for combining, but we are not going to go into those. Two aspects, that is growing a forest of trees and using randomness in building each classification tree, they lead to actual evaluation of whether this method is a good method or a bad method. It also helps to make the algorithm robust to noise in the data set, and compared to single decision tree, the random forest approach decreases the variance in the prediction results for malware detection. So this also, random forest also is close to human approach for classification, where we try to use where we try to structure the data which is to be classified and then apply different decision trees. That's what random forest I would put as based on. The ANN, artificial neural network, is a computational model inspired by the biological nervous systems. So this is presented as a system of interconnected neurons that compute the values from input. The figure here, diagram, shows the natural neurons consisting of dendrites and cell nucleus, axon, and synapse. And the bottom diagram shows the artificial neurons, where the inputs, the nodes, the weight functions, neurons, and the outputs as these things are labeled. Neurons in ANN, they are termed units arranged in sequence of layers. So typical, the way in which ANN works would be in terms of layers. We'll have input layer as shown in color coding, input layer, hidden layer 1, hidden layer 2, and so on, and there'll be an output layer. It is the hidden layer which would do the job of identifying the characteristics and taking them through appropriate classification to present the output in appropriate perspective. So input layer accepts the inputs in several different formats. The hidden layer presents in between input and the output layers, performs all the calculations to find hidden feature vectors, hidden features and the patterns, and the input then goes through a series of transformations through hidden layers, which would finally result in the output that is conveyed using this layer. So this transformation also is to be done based on some function, which would be a transfer function. And typically an ANN would be characterized by the use of a particular transfer function, which is the computation on the weighted sum of the inputs and including some bias to be applied to the inputs to transform. And there have been numerous attempts at using ANN for the malware detection. We also saw the ensemble methods as being depicted as the trends of the past. So still I'm talking about the conventional machine learning methods applied to malware detection. These improve upon the previous methods, and so they have been often used. Ensemble methods construct a set of Bayes classifiers and then classify new samples by taking a weighted vote of the predictions of the Bayes classifiers. So these methods are often used to overcome the instability and improve the prediction performance of the previous classifiers. And an ensemble framework would consist of what is shown in the diagram, if I have the diagram. No, I don't have the diagram, but it can better be viewed as something consisting of individual Bayes classifiers, conclusion combiner, and these two individual Bayes and conclusion combiner sort of applied by the ensemble methods, which are known as bagging and boosting, which are typically two popular ensemble learning algorithms. And in malware prediction, and ensembles of classifiers have also been employed to further improve the prediction accuracy, that is the prediction of different malware families. But still, the conventional machine learning techniques. With this slide, what we move to conclusion of the talk, the deep learning based classification. And it's here that the techniques are often referred to as the modern application of modern machine learning for malware detection. So if you read the white papers of different anti-malware companies, you would see them proclaiming upfront on the first page of the white paper itself. They would proclaim that we have started using deep learning for our malware prediction, because they have to sell. So that's where we see this trend as the modern machine learning for malware detection. So though ML-based approaches in security have done a good job at detecting new threats, and they also come with substantial development cost. That is, for handling the features, the kind of approach we talked about, where a large set of features are to be created, then something is to be selected from them, and then they have to be classified using different sort of approaches to analyze them. That basically creating and curating a large set of useful features, that property of the executable that can be used to distinguish between the goodware and the malware, it takes significant amount of time. It takes significant expertise from malware analysts and data scientists. And it's here that, therefore, the deep learning, new frontier in data mining and machine learning, which had good impact in other fields, typically in computer vision. Computer vision related applications actually showed, their deep learning showed good promise. But then the researchers started thinking about, why can't we use the same technique in some way in case of sort of malware detection? And that's how they were started being used. It's therefore part of or subfield of the ANN, artificial neural network, and able to learn without human supervision. So we saw that in the third or fourth slide when I talked about panorama of machine learning. I said this is kind of giving you a global view of machine learning. Even if we are from the field of information security, let's say I don't belong to machine learning, then the idea behind showing that panorama was to convey that now when we talk of applying techniques to security, we have to be dependent on these techniques. The techniques which try to learn automatically, as we had emphasized then, without getting into supervised or unsupervised learning. Therefore, we say here, learn without human supervision, drawing from data that is both unstructured as well as unlabeled. What is a multi-layered deep learning architecture? This is of superior ability in feature learning, helps reduce features required for malware detection. When we think of deep learning, question would come, why deep learning? And the objective is what I mentioned earlier as the limitation, large number of features. So here we would have first advantage, reductions in the features to be processed, employs a layer-wise pre-training, that is pre-training multiple layers of feature detectors from lowest level to the highest level to construct the final classification model. This feature overcomes the learning difficulty. And there is a beautiful paper, if at all you are interested in going further in this particular field, not so very old, because I'm showing that as a 2019 paper, which talks only about a survey of deep learning methods, not only for malware detection, but for cybersecurity. And you would find two popular areas. Remember earlier I said that ML for security is coming up as a course of itself, and I said there are three main components. So those three main components are as follows. First, try to look at the machine learning techniques, understand the machine learning techniques in general, see how machine learning in general can be applied to the security problems. That's what is described very nicely in this paper, which says survey of deep learning methods for cybersecurity. Then the second component would look at applying machine learning techniques to two components. The first component is malware and vulnerability analysis, and the second component is the IDSS and IPSS, intrusion detection and prevention systems. So it's there that the machine learning applications are widely found. So I mentioned two components. The first component was basic machine learning. Second component, looking at both classical as well as modern machine learning techniques applied to two different aspects: malware analysis and detection, including vulnerability analysis and detection, and the second aspect is intrusion detection and prevention. The third component I am not yet mentioning. I'm keeping it close to me only as of now. We'll see what is the third component, very important in the malware for security studies in general. So that's why, the reason I digressed a bit was with reference to this paper, the paper by Berman, which talks about deep belief network, recurrent neural networks, CNNs, GANs, recursive neural networks, all this sort of compared with respect to applying them to cybersecurity and applying them to malware detection also. It is observed that the DL architectures, and in particular the CNNs, can do a good job detecting malware simply by looking at the raw bytes of the Windows PE files. An overview of a CNN classifier is shown in next two slides, which can best be seen from the figure also, the figure which I'm going to show you here. If you look at the first part of the figure, you see Windows PE file structure with different components: DOS header, PE header, optional header, data directories, section table, and code, imports, data, and different sections. That is sort of processed. We have the raw byte representation of the executable. Absence of any structure that might exist. So we don't want any structured information. That raw byte is taken as the first step in this CNN classifier. Next, what we do is this raw byte sequence is embedded into a high dimensional space where each byte is replaced with n-dimensional vector of values. This embedding allows the CNN to learn relationships. Remember earlier when I talked about the NNs also, I said transfer function, weighted transfer function is used. That's the step. The embedding step allows CNN to learn relationships among the discrete bytes by moving them within the n-dimensional embedding steps. As for example, if the bytes, we have two bytes, let's say E0 and E2, if they are used interchangeably in the PE file, then CNN would learn from that these two bytes should be moved closer together in the embedding space so that the cost of replacing one with the other is eventually small. That is what is done as the second step here. The third step, it says, it's shown here as sliding convolution filter, brings in some notion of convolution filter. We don't know what that is, over embedded byte sequence. Let's see here what is the third step. It says we perform convolutions. So as I said, we don't know what is convolution, which is a linear operation that involves the multiplication of a set of weights with the input over the embedded byte sequence. Whatever byte sequence we saw, the weights with the inputs, they are sort of multiplied as a linear operation, and that's what we treat as convolution. So in simple terms, this would be meaning if it is done across the entire training set, the convolution filters are applied across the entire training set, they would start learning the characteristic of certain sequences. So in simpler terms, it would mean you would slide a fixed length window across the entire vector space and across the embedded byte sequence, and the convolution filters would start learning about the important features from across those windows. So once we have scanned the entire sequence, if we go to the figure, we would have these filters prepared. We can pool the convolution activations to select the best features from each section of the sequence to pass along to the next level. So in practice, the convolution and pooling operations, they would be repeated together in a hierarchical fashion to aggregate the features into smaller number of high-level features. And then we would use these aggregated features from our pooling as input to fully connected NN, which would be used for prediction purposes, which classifies the, not prediction, sorry, which for classification as PE file sample or either PE file sample to be classified as either goodware or the malware. So that was an abstracted, highly abstracted view of CNN classifier, which would be used for malware detection. Again, this is nicely presented in one of the anti-malware sort of white papers only. Lastly, after CNNs, if you look at a very recent paper, this is 2021 paper, which says comparative study of adversarial attacks to malware detection. I have not talked about adversarial attacks as of now, to malware detectors based on deep learning. And this is actually an ebook chapter. Let me not refer to that as a paper. It's actually an ebook chapter. So I'm not referred here, I've not mentioned here any journal name, but if you do a Springer ebook titled Analysis Using AI and Deep Learning, you would see this paper, and it talks about GANs. So generative adversarial networks are a class of algorithms used to create synthetic data by continuously improving this statistical model of the data distribution. Data created, there are two algorithms used here. So it's like a game theory, game playing kind of application. Data created by one algorithm would be constantly refined by the other until it not only sort of resembles real data, but ideally it is indistinguishable from the real data. And this refining technique uses two sort of algorithms. One is known as generative network, which creates the new data, and other is known as discriminatory network. The job is to discriminate between the characteristics. So critiques the new data created and provides feedback that is used to refine the generated data into something that is indistinguishable from the real input which was given to the data. So it is this creative, critical nature of the two networks which complement each other, which makes it adversarial to sort of create the new real data. So I am able to get a sample from a Windows PE file, which would appear like a true malware. So if I then receive actual sort of during my testing phase, if I receive a sample which is appearing like a real, like what I have created, would tag it as a malware. So through repeated cycles, the system would rapidly create new synthetic data, and applied to creating malware, this process ultimately creates new files that would contain malware, which are all, with all intents and purposes, indistinguishable from real data files, and these are used for detection. Remember, the problem why we thought of new ML techniques for malware detection was what I mentioned earlier: modern obfuscation techniques, the metamorphic techniques, and polymorphic techniques, where the file keeps on changing the behavior. So we use these techniques to be able to identify the malware. What next? Next is something on feature clustering. We just now talked only about classification. We also see unsupervised learning technique, clustering being used, people working on using clustering for malware detection. I have simply mentioned here what is clustering. Basically, unsupervised learning, partitioning a given data set into clusters without putting them into different classes, as we discussed in classification. This would be based on predefined distance measures, so that what is to be put in one cluster would be determined based on this distance measure. But in malware classification, this would mean you want to put into clusters which are benign, clusters which are not sort of benign, and so on. There are two methods used: partitioning and hierarchical clustering. I'll not go into. I have not even put here any information about that, because relatively one sees very little literature on using clustering for malware detection as compared to the DL-based malware detection. ML tools and data sets for, I know I have kept one part still pending. Remember earlier I said I showed you two components of any topic on ML for security. The third component I kept hidden. I'll still keep it hidden, but let us just look at the malware tools and data sets for malware detection. So this appeared in one of the recent papers. The reference of the paper is unfortunately hidden at the bottom. I've cited it, but by figure somehow I could not manage. So the label is not appearing in the bottom part. But you could do an IDR, you could do a Google string on only IDRBT. So IDRBT plus malware detection, and you would land up on this paper only, which talks about various tools for detection, tools for online scanning and sandboxing, static analysis tools, dynamic analysis tools. So with the intent of each tool, what that tool is used and which environment it is used, including something used for Linux, something used for APKs, something used for a typical type of file like P or COF files, and so on. So nice hierarchy is shown here. As I said, my job here is to point out the literature. I showed you do a Google on IDRBT plus a malware detection, and you would land up in this paper. The same paper talks about the data sets used for experimentation in malware, along with the citation numbers also in that paper. They don't have anything to do with this presentation. Talks about the description of the data set also. So again, this could be referred to in that paper. I'll not talk about it. What are the concluding remarks? And that's where the third component comes in. The third component is adversarial machine learning. So no matter what machine learning technique you think of, whether it is conventional, whether it is conventional machine learning based, or modern deep learning based technique for security in general, or for malware detection, the adversary is always there to learn from you. So whatever you do, adversary would say, I would also learn and I would apply it for my benefit. So there is third component of such a course which is always required to be taught of. What I was mentioning was any ML course for security would be constituted of three components. First one would be general machine learning. Second one with two components: machine learning for malware analysis and detection, machine learning for intrusion detection and prevention. And the third component would be adversarial machine learning. And there is a lot of literature on adversarial machine learning. In fact, just to share with you, day after tomorrow only, there is going to be one more talk on adversarial machine learning at one of the FDPs there itself at Indore. So it's the study of machine learning vulnerabilities in adversarial environments. So one can find literature on practical attacks against machine learning, everything: machine learning, anti-malware, spam filter, network intrusion detection, image classifier, sentiment analyzer, whatever software which is using machine learning, you would find the attacks against those. And this is the study, therefore, of finding out how vulnerabilities in ML systems can be exploited for malicious purposes. It's a machine learning technique that attempts to fool models by supplying deceptive input, causing a malfunction into ML model. So when I cause malfunction into my ML model, I would know how the ML model would behave when the actual adversarial malfunction happens. So it's a fast-growing area of research that studies the design of ML algorithms that are robust in adversarial environment. It's the study of how adversaries would craftily manipulate legitimate inputs, which may be imperceptible, indistinguishable to human eye, but can force a trained model to produce incorrect outputs. It's the study of susceptibility of ML models in adversarial settings and corresponding countermeasures. So when we talk of this, entire study of using ML methods for malware analysis, we also have to look into the adversarial ML for malware analysis, because I mentioned earlier, it is applied to every category, whatever category of where you apply ML, the adversarial machine learning, you will find things applied there also. So this is study of those techniques, and then only one would be better equipped to deal with malware detection using machine learning approaches. That's where I would like to stop. As I said, I always say to teach is to learn twice, because while I would be teaching this, I would still be learning something. And therefore, thank you very much. Over to you,
Thank
madam.
you. Thank you, sir. Sir, can we call few queries of the participants?
Definitely.
Yes, Ravindra Sharma.
Good
Ravindra.
afternoon, all. Yes, good afternoon, ma'am, and good afternoon, all. I am Ravindra Sharma from Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore. Sir, thank you very much for this informative lecture. And now I'm able to connect the security aspect with ML. Thank you, sir. Sir, I have some query
Please.
regarding this.
Please.
Sir, can we think, or how can we think about the role of machine learning at lower layer of security or physical layer security? Can we think about this?
Well, that's a very good question. So, basically, I don't work in physical layer security. Let me put a disclaimer up front. And
Yes.
therefore, the mechanisms used there, if you think in terms of in retrospection, if you try to see this in retrospection, then machine learning or whatever we talked of would be applicable basically on the mechanism used for deriving security. As I showed in the first or second slide itself,
Yes,
that
sir.
was the purpose why I showed that. I was trying to emphasize there that ultimately the goal of the attacker is to attack the mechanism and
Yes, sir.
prevent you from getting the attributes which you want to get it.
Yes.
That's where, if you think of physical layer security, and I'll cite a very simple example, even though I don't work in physical layer security, but I'll give a simple example. When you think of using a particular sort of technique in the radio chip, think of CC2420 or CC3420, which are implementing Zigbee in the radio chips in a typical IoT environment. They
Yes, sir.
have a entire security suite built in, use ciphers for encryption, message authentication, that is data integrity, and for entity authentication. When I think of these three attributes, and when I think of plain encryption, decryption, there is no way by which the adversary is going to be able to exploit any aspect in order to attack it. Because remember, we talked of the adversary successful when there is some part of intelligence required to be built into. If it is pure simple mechanism, like I never talked of adversary being able to attack an encryption algorithm.
Yes, yes.
Have you read anywhere which says that a cipher was broken using machine learning algorithm? I'm
Yes.
afraid that would not have been read. What we read is an application which is being attacked, like malware detection. Malware ultimately is a software.
Yes,
That's where machine learning is used. So my feeling, although this can be cross-checked, because as I said, I don't work in physical security, and I would want to first verify what are the mechanisms used there to give me the security. As long as I'm using plain, simple encryption, decryption, and the basic features for being given the security attributes, I don't think adversarial ML would succeed there. That's how I'd like to put it.
Okay, sir. Thank you, sir. Sir, can you please suggest any hardware or software tools so where we can implement ML concepts, sir? For
I think
learning? Yes.
No, I didn't get the question basically.
Can you please suggest any hardware or software tools so where we can simulate ML concept to learning purpose?
I mean, I would not suggest any tool, but you could straight away start with the Python libraries. That would be the best place to implement machine learning algorithms. The most simple one. Why Python libraries? Because my personal take is that Python is something which is not meant only for CSE people. So if you want to straight away work in simple machine learning, then
Yes, sir.
best one would be to start with Python and the libraries built into there. Work on machine learning concepts. Like I'll think of classification
Yes, yes,
and
yes.
use Python code to see how classification can be done, how clustering can be done. And gradually that could be your stepping stone towards more complex things in machine learning.
Yes, sir.
Am I answering your question?
Yes, 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 sir. Thank you, sir. Thank you,
Okay,
sir.
thank you.
Thank you, ma'am.
Okay, questions from other participants. Someone raised hands before.
Hello to all. Good afternoon.
Yeah.
This is Mosmi Verma, sir.
Yeah.
Sir, I just have one or two questions.
Please.
When you explained about the layering of ANN,
Hmm.
neural network,
Hmm.
so sir, in that you explained by showing 3 layers, and the middle one layer is the hidden layer. There was hidden layer 1 and hidden layer 2, and you explained that these layers are these layers are used for computational purposes. So are all the hidden layers used for computational purposes, or
Yes, they, no,
yes, sir.
sorry to interrupt you. If you have noted, I said that the purpose of hidden layer is to extract the characteristics, the attributes in the input, so that classification, the purpose for which it is meant for, can be done. And therefore, I didn't. I mean, when I said hidden layer 1, hidden layer 2, that was only a sample. It'll be dependent on the particular model which you have used as to how many hidden layers you have. The diagram, if you have noted, in case of deep learning diagram which I showed, was showing 4 different layers.
Yes.
So it will depend upon the features which I want to process as to how many layers to use. But the basic goal would be to use a function which would help me in transforming the input from the raw bytes into something which can be associated with characteristics, classification.
Okay, fine, sir. You mean to say that these layers can be increased or decreased depending upon the
Absolutely.
functionality
Absolutely.
they are used
Yes.
for? Okay.
Yes.
Sir, one just a small very question.
Yeah.
That definitely the conventional method of for protection purposes, in comparison to that, machine learning is far better than those conventional methods. But sir, is this using means the security against malware providing by the help of this machine learning, does it assures 100% accuracy, or some other way it can be improved?
Very, very difficult to. No, I mean, that second part of the question was interesting. You said other way it can be improved. When you talked about the first part, 100% accuracy, I'm afraid nobody would be able to point out that it gives me, because this entire business, if you see the malware growth, there is a long sort of topic on malware growth, which I did not discuss in this case. But if you see how attackers are using automated malware creation, I mean, you would not be able to have something which will give you 100% protection at every instant against the new malwares which are being generated. So this is a kind of endless process. So that first part, I think, can be answered in no. But what was the second part? I forgot.
So is there any other way to improve that?
Yeah, is there any other way to improve upon that? No, as of now, machine learning is appearing to be the most promising sort of aspect, because there are no other. Basically, what you want to do is you want to build intelligence into the machine. Why do you want to build intelligence? That's why if you have noted my talk, rather than going into the actual mechanics of a particular operation like deep learning, what I tried explaining was the motivation for why we want to go there. And the motivation comes out to be the speed at which the speed and the size of the data which is being generated. So because manual it is not possible, what I would need to do is I'll have to build my intelligence into machine only. And when I am building my intelligence into machine, no matter what mechanism you use, whether you use supervised, whether you use unsupervised, whether you use ensemble methods, machine learning is so vast a field. It encompasses all these techniques. Wherever you go, you would end up using machine learning. So I don't think there could be any other approach which would better them. You'll have to be dependent on machine learning.
Yeah. Thank you so much, sir, for answering my questions, sir.
Please. Thank you for asking questions. That's how I should say.
Thank you.
You do not know. I mean, you could be a teacher, but a teacher gets a thrill only when questions are asked. Otherwise, it becomes pretty dull. Yeah.
Is anyone else is having any query?
Inwal Sahab, I have a question now.
Please, sir.
Okay, the question- okay, thank you very much for this extensive tutorial on machine learning
Yeah.
with flavor for malware detections and also some flavor of deep learning. Now, for our normal PCs that we use at our home, I mean, what we should do? Because if we implement all these things, the machine becomes slow. So, I mean, what one should do for a normal person who is using PCs at his home, laptops at his home? The one thing you will say, don't download anything. I mean, that is one thing, and it's very simple. Don't
Yeah.
download any file, don't download any picture, don't download any video. I mean, that is one straight way.
No, it's
But,
like it's like I would say, you bury a hole which is 20 feet down the ground and put
yes,
your
yes.
machine there, and then you are
So,
secure.
so that cannot be done. So,
Yeah.
nobody-
Yeah, I think the only way is to be as aware as possible. That's how I'd like to put it.
yeah,
When I
think
put
that's the
myself
only
into
thing.
the role of a user,
Yes.
distincting myself as somebody who works in this area. If I try to put in the role of a user, the only solution is to be as aware as possible, because I'll not be able to match the anti-malware companies who build extensive anti-malware protection mechanisms to protect somebody, to protect a user, PC user, against malware attacks. So I'll not be able to build all those things here. So I'll be dependent on the anti-malware vaccine only. But then, as some question which was asked just now, like if I use anti-malware in my machine, would I have 100% protection? The answer is no. So how do I try to protect myself? And the question would be to be as aware as possible. And in my experience, I would say, just to share with you, if at all time permits, and this is an experience which I'm sharing with you, Professor Vyavahare. Before I went to US, I had not used Mac OS at all. And it was to the extent that when I went to US and I was given a Mac machine, because the university did not have any Windows machine. So I was given Mac OS machine, and it was too uncomfortable for me to work on Mac OS. But then once I got familiarized, now my experience says that the life is pretty cool, because you never have to bother about these kinds of very frequent attacks and those things taking place. That's a personal experience. But I also shared here, I also made a statement which said in 2020 and 21, the attacks on Mac OS were found to be much more. The frequency was found to be very high. That's an observation. I already said I don't know the reason, because this is what I read in some article only. So my personal experience is that if you are using Mac OS, then perhaps the life is much more cool. That's what I feel on this particular front.
For
Am
the
I
Windows
answering the question?
people, what is your advice?
Yes, sorry.
For the people who are using Windows,
Yeah,
what
so
is
only
your
thing is to be very much aware, never trust any site you are visiting, because you have to look at what are the sources of malware creeping into your machine. The sources are the same, whatever you said earlier. If you are downloading something, be very sure about downloading and so on. I mean, simple reason why Mac is so secure, because Mac doesn't allow you to download and install any software unless from Mac repository, which has so many protection mechanisms built into. Only after you download something from Mac library, then only their store you would be able to download. So that's what makes it more secure. Windows, if we try to simulate the same behavior, then we would be surely to be secure. That's the answer.
Okay, thank you very much. It was
Thank you,
pleasure
sir.
listening to you.
Thank you, sir.
Okay, thank you, sir. You have explained machine learning techniques with perspective of network security very nicely and exhaustively. Thank you so much for sharing your personal experience. It was really an interesting one. In fact, it has guided research direction to participants looking for their PhD. Thank you, sir, for your kind consent and spending your valuable time for this FDP. Thank you so much, sir.
Thank you very much. Thanks to everybody. And Professor Vyavahare, it was an honor to be having you as my, in my audience, I must say. It's always a pleasure to be interacting with you.
The
Thank
learning
you,
never
madam.
stops, you said, so I have to learn now new things.
Absolutely. Yes, yes, yes.
Okay,
Thank you very much. Thank you all participants for being with this course and for being in this FDP. Madam, can I call off now?
Okay, sir.
Yeah, thank you.
Next 3 बजे ना रक्षा?
हाँ सर, 3 बजे से।
अच्छा रक्षा, मेरे को ना इसका जरा ये भेजो, ईमेल कर दो क्या शाम को कभी? टाइम टेबल मेरे पास है नहीं अभी।
ब्रोशर?
हाँ नहीं, टाइम टेबल मतलब रोज के इसका किसका है वाला वो, हाँ वो ब्राउचर मतलब।
सर ब्रोशर में सेकंड पेज है, वो मैं आपको अभी भेजती हूँ।
हाँ भाई देना, आराम से भेजना है ना।
ठीक
चलो
सर,
ओके,
ठीक, ओके
सी यू
सर,
एट
थैंक
3
यू।
o'clock, बाय।
बाय सर। So the session will be resumed at 3 p.m.